So today, as promised, I'm going to do some theorems on the behavior of solutions of ODE. Okay, so that's what we are going to deal with. But before that, I would like to tell you something about my yesterday's class. So in yesterday's class, in one of the examples where I have taken this equation, and I was considering two fundamental set of solutions. Then, while comparing this with y double prime, px y prime plus qx y equal to 0, I told you that px and qx are 1. It is not like that. If px is 0, probably you would have figured it out. Okay, while the exercise where you can uniquely determine P and Q in terms of your fundamental set of solutions. In that particular exercise, I told you that Px and Qx are 1. But in fact, if you compare this one with this, then your Px is 0 and Qx is 1. Okay, so that is one thing. And in another exercise where I was dealing with this method of variation of parameters, what I did, I think while writing the final answer, instead of roping in this term, like something like ln, I have already worked it out. But in the final answer, probably I had written 1 plus x only. Please correct that. Okay, if you have noted it down wrongly. Okay, fine. So today I am going to do like this behavior of solutions of ODE. So this is what we are going to do. So basically, we are going to deal with your second order linear equations. Okay, second order linear ODEs, and of course, we are going to concentrate on homogeneous. Homogeneous, because you know that even if you are going to deal with non-homogeneous equation, so then finding the particular integral, it is not that difficult once you know a fundamental set of solutions from the homogeneous counterpart, and then you can completely solve that given differential equation, right? So that is why we will be more interested in the homogeneous counterpart. Okay, so now you may be asking me why we are so much interested on the behavior of these solutions, right? Now, again, like say, as I have told you that now you are no longer students of BSc and MSc. So earlier, many of the things we did only for the sake of academics, kind of like say for the sake of exam or something like that. Okay. So can someone tell me whether you have done this before or not? Can anybody tell me? Behavior of solutions. Did you study this part earlier?
Yes, sir. I have done it in MSc.
Like Sturm separation theorem, all those stuff, Sturm separation and comparison theorem.
Yes, yes, same.
Everybody studied, or
Yes.
Is there a no answer here?
Sir, I haven't studied.
Okay, so anyway, even if you have studied it earlier, like say, I'm going to describe everything in detail, okay? And okay, fine. So now let us come to the motivation behind this. Okay? So now you know that, say, suppose, let me take the very easy example here. Okay? So you know that your sin x and cos x it constitutes a fundamental set of solutions here, right? So now, if I want to plot it, so then my solution curve, you know, I mean, it's very easy. It is going to look something like this. It is going to look something like this. Okay. So if this is my x-axis, this is my y-axis. I am not even bothered about the amplitude here. So this is 0, pi. This is 2 pi, 3 pi, and so on. Right? So this graph is nothing but y equal to sin x. Okay? Now, what about, say, suppose I have something like this. Okay? So then, can you tell me one solution of this?
Sin 2x cos 2x.
Sin 2x cos 2x. Okay. So let me take the sin 2x part. Okay. So now, if I plot that sin 2x part, then my solution will look something like this, isn't it? Is it okay with everybody? So this is y equal to sin 2x. Okay, fine. So far so good, right?
Yes, sir.
Yes. So now you have seen that in both the cases, like say whenever I am taking a differential second order differential equation like that, in both the cases, the solution is oscillating, right? The solution is oscillating means it is crossing the x-axis. In this particular case, I mean, it is going to cross x-axis in finite number of times, right? Is it okay? Fine? Isn't it? And same, you can see for the first curve, I mean, which is sin x, here, what was happening? See, here, what is happening? The solution is vanishing at certain points. Right? Okay? Isn't it? So,
Yes, sir.
yes?
Yes.
So, what is happening? So, that means this one, where I have, like say put a cross here, they are nothing but the zeros of the solution, right? They are nothing but the zeros of the solution. Is it okay with everybody? Fine?
Yes, sir.
Yes. So now, in the first case, you can see that the distance between two consecutive zeros, is pi. Right? Is it okay?
Yes, sir.
Fine. So this is the
Yes, sir.
first. This is the second case. So this is the distance between two consecutive zero. And now, say, let me the period. Say, suppose I instead of suppose if x at x represented time. So then, see one complete period, it will be done at one time, 2 pi time, isn't it? Is it okay for the first graph?
Yes, sir.
Isn't it? So for the first graph, the period is 2 pi. Okay. Whereas for the second, what is happening? The distance between two consecutive zeros, is what?
Pi by 2.
Pi by 2. Distance between two consecutive zeros is pi by 2. And again, here period is pi. Right? So that gives you an idea. That okay, suppose I have a differential equation of this form. So then what is going to happen if I consider it as a third case? So the distance between two consecutive zeros, it is going to be fine. Is it okay? Isn't it? And period is going to be 2 pi by omega. Is it okay with everybody?
Yes, sir.
Is that
Fine, fine.
Yes.
See,
Yes,
if
sir.
we are interested in the zeros of the solution, if we are interested on the zeros of the solution of a given differential equation, right? So, in order to find out how many zeros, whether zeros are finite in number or zeros are infinite in number, and how they are behaving, so we need to study the solution curve, right? So basically, we need to study the behavior of the solution. That is why it is important. Okay. And now here what was happening. So here you have seen that the coefficient of y in all the three cases, they were constants. So that is why our life was, much more simpler mathematically, right? We were able to figure out, how many zeros in a particular interval. What is going to be the spacing between those two zeros, right? Isn't it? But the thing is that if I consider an equation of this form, where the coefficient of y is a function of x, of course, these are also function of x. They are simply constant functions earlier, whatever cases we have taken. But here, if I consider something like this, and if I want to study the behavior of the solution based on some properties of qx, it would be much better. Is it okay? Fine. So that is where the motivation of this comes from. Okay. So let me show you one particular slide. Over there, what I'm going to do, I'm going to consider two equations. Okay. So the first equation is simply going to be this, and I have already plotted the solution graphically. But in the second case, what I'm going to do, I am going to consider this equation. Okay, so then you can see that your qx is not a constant here, and I'll see how the solution behaves under certain initial conditions. Okay, and of course this one, it will be extremely difficult to solve analytically. Maybe we'll have to go for power series. I don't know, but I can solve it numerically pretty easily. Okay, so what I am going to do, I am going to show you the plots. I am going to show you the plots of the solutions of this equation and this equation. Okay, so that is what you are going to see in this slide. So this is what is happening. See, this one is nothing but the solution of this problem. Okay, u double prime plus u equal to 0. And at u equal to 0, x equal to 0, the value of u is 1. So that is why the solution is starting from this point. Okay, and you know that eventually you are going to get a sine wave here because okay, so they are plotting cos x as the solution, right? So here this is the solution curve. And again, if you draw a line here, at y equal to 0, you will see that the solution curve is crossing the x-axis at certain number of points here, and you already have an idea what those points could be. Okay, fine. And of course, here qx is equal to 1. So now let me move to the next one. So that problem where qx was 1 plus x. And again, this solution also starts at a value of u equal to 1, corresponding to the point x equal to 0. Now here, you can see that the phenomenon is different here, right? In the earlier case, so please have a look at this. So I'm going to come out of this and then I'm going to talk to you. Okay? So you have seen both these solutions. Okay? So here again, you can see that like what was happening in the first case. So maybe I can give you the solution something like this. It was like, so it was something like this. Okay, so in the first case we had seen that like the spacing between two conjugative zeros, they were uniform, right? The spacing was the same for all the zeros. Is it okay? But in the second case, you can see that as x tends to infinity, what happens is spacing between two consecutive zeros, it is getting smaller and smaller, right? Okay. So now you have seen that although both the solutions were, kind of oscillatory solution, both were oscillatory solutions, but still their behavior was different. Is it okay? Fine. Their behavior was different. So we are going to study this kind of stuff. We are going to study this kind of stuff. I'm still expecting one question from you. Say at the very beginning, let me tell you what the question could be. At the very beginning, I told you that I'm going to consider behavior of solutions of second order linear ODEs. Okay, and a second order linear ODE in the normal form. I can write it as this. Okay, so now it's up to you to ask me the question. Yes, I'm listening. You can ask me. What could be the question?
If sir ux is 0 and px is non-zero, then what happened?
Ux is 0.
In both the examples, actually, we are considering px to be 0.
Exactly. That is the point. That is the point I want to make. Yes, yes. The question I was expecting is that, like, say, I am considering at the very beginning, I told you that I am going to consider a second order linear equation, and its general form, its normal form is this, right? Whereas the examples that I have shown you, it pertains to only equations like this, right? So that is the point I am going to make a bit later on. Okay, so if I don't make that point, you please, remind me about it. Okay,
Sir,
so
this problem we can also transfer this into normal form. Then we can
Which
get
one?
our result.
Which
Y
one?
double dash plus pxy dash plus qxy.
So you okay? I got your point. You are saying that I can reduce this equation into this form, right?
Yes, sir.
Yes. But what after that? Okay, I have reduced it. Again, what is the guarantee? What is the guarantee that that studying solution of this equation is going to be similar to studying solution of this equation? Okay, this kind of equation. What is the guarantee? Okay, I am going to answer to that question a little while from now. Okay, fine. And that is where it's going to bring me. The first of the three theorems that I am going to prove today regarding the nature of solution or behavior of solution. Okay, fine. And slowly you are going to find the answer to all these pertinent questions. Okay, so let me show you the theorem. After that, I'm going to come back to this. So this is the first theorem, the Sturm separation theorem. Okay, Sturm separation theorem. So please have a quick look at that, and then I'm going to prove it. So what does it say is that suppose I am considering a fundamental set of solutions. So basically, y1 and y2 are two linearly independent solutions of the second order homogeneous linear equation. In normal form. Okay. So then the next two lines are very crucial. Then the zeros of these functions are distinct and occur alternately, in the sense that y1x varies exactly once between two successive zeros of y2 and converse. Okay. The first thing that they are saying that the zeros of the solution functions, they are distinct. Okay, And secondly, they are saying that the if you consider two successive zeros of one function, then the other function vanishes between those two successive zeros. Okay, and vice versa. Okay, proof. So let me first again, before proving, let me again get back to the statement of this theorem. Okay, so I have been given a differential equation. This one. Okay, I have been told that y1 and y2 they are linearly independent solutions. They are linearly independent solutions. Okay, then I have to what I have to prove that they are distinct in one sense. They are distinct. They are distinct, and like say, if you consider, say, suppose this is x-axis. Suppose this is x-axis. If you consider, say, x1 and x2 to be two successive zeros of say y2, then this y1 is going to vanish between x1 and x2 only once. So basically, you cannot get two zeros of y1, two zeros of y1 in this interval. Are you getting my point? Are you getting my point?
Yes, sir.
What the
Yes,
statement is all about? Okay, fine. So here, what we are going to do, we are going to concentrate on the Wronskian. Okay. So firstly, let me write down the Wronskian of this function. Okay, in the interval of definition. Okay, fine. So the Wronskian of the function, it is simply given by this. So it is a function of x, of course. It is a function of x, and okay, fine. So it is y1, y2. Maybe, sorry, let me write it in terms of. Let me write it like this so that. Yes. Okay, fine. Now, okay. Now, the very first thing that we are going to prove that they have distinct roots. I'm sorry. They have distinct zeros. They have distinct zeros. The solutions have distinct zeros. So that means they cannot have common zeros. Are you getting my point? So that means y1 and y2 cannot vanish at a comma point, right? So that is going to make their zeros distinct, isn't it? Are you getting my point?
Yes, sir.
Yes,
Right?
yes, sir.
Yes, sir.
So now you tell me, if both the functions vanish at a common point, what is going to happen?
At that point, Wronskian will turn out to be 0.
Wronskian is going to be
Their
0.
Wronskian
And in
will
that
be
case,
0.
yeah, in that case, y1 and y2 cannot be linearly independent. Is it okay? Fine. So
Yes,
that is
sir.
why
Yes, sir.
the zeros of y1 and y2 has to be distinct. And again, please write down everything once you, okay, of course you are at home now. Once you have, like say, ample time to revise my lecture. And ideally, I want you to do it on the same day. Okay, fine. So that part is done. Okay, so we have done the distinctness part. Okay. See, the next thing I am going to tell you is that the Wronskian W cannot change sign in the internal definition I. Why?
If
Sir,
change sign,
we-
then there is a chance to go 0 at some point.
Exactly. Because say, I am here, while defining the Wronskian, I am assuming that the derivatives of these functions are also continuous, right? And y1 and y2 being continuous functions as well. So eventually, the Wronskian is going to be a continuous function of x, right? And because these are y1 and y2 are linearly independent solutions, so Wronskian cannot become 0, right? Okay, isn't it? Wronskian cannot become 0. So now, if the Wronskian is going to change sign in this interval, then the Wronskian has to be 0 by intermediate value theorem somewhere. Is it okay? Fine. Which cannot be, because we have already proved that. I mean, again, yesterday somebody asked me about some possible solution, and please bear in mind that here the Wronskian we are dealing with, it only pertains to solution of equation. I mean, they pertain to functions which are nothing but solution of some differential equations. Okay, so that is why all the theorems that are going to be developed, it is going to be based only upon that. Okay, the Wronskian is either 0 or non-zero in an interval. So now you have understood this one, why they can Wronskian cannot change sign, right? Because if it is going to change sign at a certain point, it is going to cross x-axis. It is going to cross x-axis. That is going to make it 0. If it is 0, it has to be 0 throughout the interval, which is a contradiction, right? Because y1 and y2 are linearly independent. Fine. Up to that it is clear. Okay. So now let us assume that let x1, x2 be two conjugated zeros. Zeros of say y2. So this is my situation. So I am going to prove that the a 0 of y1 it crosses the x-axis between x1 and x2. That is what we are doing. So that means your y2 x1 equal to 0 equal to y2 x2, right? Y2 x2. Okay, fine. And then what is going to happen? This Wronskian given by say this equation 1. So from A we can say that at x1 and x2 your this Wronskian simply reduces to your let me write it simply like this. This is equal to simply y1x y2 primes. Is it okay with everybody? This is only at these 2 points. Is it okay?
Yes, sir.
Yes? Okay. So now, again say, I mean, because y1 and y2 are linearly independent, I mean, they cannot be the trivial solution. They cannot be the trivial solution because otherwise this set is going to become linearly dependent, right? So if I mean y1 and y2 are not 0, so definitely I can assume that I mean y2 is greater than 0 for all x belonging to this interval. Is it okay?
Yes, sir.
Yes, fine. I can easily see it has to be either greater than 0 or less than 0. So anything is going to work. Is it okay? Anything is going to work. I could have taken less than 0 also. Then also the way I prove this theorem, that is going to be very okay. So that means what is going to happen? See, so that means your y2 curve, if the curve of the function y2, it is going to lie above x-axis in the interval x1 and x2, right? But what is happening here? X1 and x2 are zeros of y2. So obviously, the function being continuous, it has to rise here. It has to rise here and then rise here at x1, okay, and fall here at x2. Are you getting the point? Isn't it?
Yes, sir.
See, right? This has to be my situation. isn't it? This has to be basic value. It is not necessarily like the sine wave. It is not necessarily like the sine wave. It could be something like this. It could be something like this. Again, you can have something like, but anyway, it is not exactly the sine wave. You're getting the point, right? Okay,
Yes.
fine. So at x1, it is rising, and at x2, it is falling. Otherwise, I cannot get a situation like this. Isn't it? Only then the function is going to cross the x-axis at those 2 points. Assuming that in the open interval x1, x2, the function is always positive. You got my point?
Yes, sir.
Yes?
Sir.
Okay, fine. So, therefore, for this, what must happen? Your y2 prime x1, it has to be greater than 0, and y2 prime x2, it has to be less than 0, because at those 2 points, the function has to be, once in x1, it has to be monotonically increasing, and in x2, it has to be monotonically decreasing. Okay? Fine?
Yes, sir.
Yes, that is why I told you. That please go through the chapter on how derivatives affect the shape of a graph. So if you have done it, these concepts are going to be pretty straightforward. Okay, fine. So now, again, we had already proved, or we have already stated, that the Wronskian cannot change sign in that interval. In the interval of definition. Okay, fine. So, I mean, what we can do? We can easily assume that the Wronskian is positive. Even if it is negative, also it is going to work. So suppose the Wronskian is positive throughout the whole interval. Not necessarily only in the open interval x1 and x2. Throughout the whole interval of definition. Okay, let us assume that. Let us assume that W x is greater than 0 in I, where I is the interval of definition of these two solutions. Is it okay? Fine. So then what is going to happen? Now you look at this. You look at this expression. This expression happens only at x1 and x2, right? So now we have already found out that this y2 prime at x1 is positive, right? So if the Wronskian has to maintain its sign, if it is positive, then y1x1, it must be positive. Is it okay? Fine?
Yes, sir.
Yes? Similarly, what is happening? Y2 prime x2, that is negative, right? So in order for W to maintain a positive sign, so that means y1 at x2 must be negative. Fine? So that means y1 at x2 must be negative. Is it okay?
Yes, sir.
Yes, sir.
Fine? So if this happens, then what must be? Y1 being a continuous function by intermediate value theorem, right? Since at the end point of that interval, I mean x1 and x2, it changes sign. So that means somewhere in that interval, it must vanish. Is it okay?
Yes, sir.
Fine.
Yes.
So my situation, I mean, if I want to draw the graph, my situation is going to be something like this. See. Okay, so then I will have some situation like this. It is going to vanish at some point x star in the of an interval x1 and x2. Fine? Am I done? Am I done?
We have to show there is no other zero in that x1,
Exactly.
x2
Exactly. Exactly.
of
What is the
y1.
guarantee that there is only one zero y1 in that interval x1, x2? Is it okay? Fine. So see why that cannot happen. Let me tell you. See, suppose it has more than one zero in the open interval x1, x2. Like suppose it has say two zeros. So suppose I have one zero here and another zero here. Okay. So then what is going to happen? See, the way we have proved the theorem, I have taken firstly the conjugative zeros of y2, right? I could have started with conjugative zeros of y1, right? And I would have arrived at the same conclusion, isn't it? So had I started with y1 at these 2 points, then this proof is going to lead me to a zero for y2 in this interval. Is it okay with everybody? Between these two zeros of y1, right?
Yes, sir.
Isn't it? So, but I have assumed that x1 and x2 are two consecutive zeros of y2. So I will get a contradiction. Is it okay with everybody?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
I will get a contradiction. So that is why it will have only one zero. Y1 is going to have only one zero lying between x1 and x2. And that proves the theorem. And please write it down systematically. Okay, when you have time. So this is about the first theorem, and it is called your Sturm separation theorem. Okay, fine. So now let me see whether I have missed something. Okay, fine. So let me do one exercise, then I'll come back to the remaining part. Okay, so you have to prove that, show that the zeros of these two functions, they are distinct and occur alternatively whenever AD minus BC is not equal to 0. Just you tell me how to go about it.
We will construct a differential equation of which these two are solutions and being
Okay.
linearly independent solution.
Yes, so they will be fundamental set of solutions, right? Okay. Yes. Yes. So then they are going to have distinct and alternative zeros, right? I mean, they have to be linearly independent, isn't it? So for linearly independent solution, you need the Wronskian to be non-zero, right? And from there, you can easily get that. Is it okay with everybody?
Yes, sir.
Yes? Okay. Right. So this is about it. Okay. So now let me come to just a minute. So maybe I simply write it as rationale behind, say, studying this one. Okay, and again, the way we have proved the earlier theorem, right? So I have proved that, like say, we assume the existence of two consecutive zeros. So there, I drew my curve like this. I drew my curve like this. Okay, fine. And and because I assume that in that interval the function is positive. Okay. So had it been negative, then I would have drawn something like this, isn't it? Right? So in many books, this kind of assumption they call it convexity condition. Okay, because for example here it is concave downwards, this one is concave upwards. Okay, so that is why they call it convexity condition. Okay, fine. So now let us see what is the rationale behind studying this. Okay, so firstly I am going to do some mechanical mathematics and then I will come back to the motivation part. Okay, fine. See, my original differential equation was this. Okay, in normal form it was this. Let me call it 1. Let me call it 1. Okay, so now suppose I would like to reduce it to this form. Okay, or maybe what I can do, so instead of writing it like this, let me write it something like this. U double prime, this equal to 0. Okay. So for that, let me use the transformation y equal to uv, where u and v are functions of x. Okay. So then obviously your y prime is going to be u v prime plus u prime v, and then y double prime is going to be u v double prime plus u double prime v plus 2 u prime v prime. This is normally it's very straightforward. Okay. So now if I substitute this here, so then I'm going to get, okay, let me write it down. U v double prime plus u double prime v plus 2 u prime v prime plus px u v prime plus u prime v plus qx u v equal to 0. See, let me tell you what I'm trying to do. I would like to get an equation in the variable u in such a way that the first order derivative vanishes. That's it. Such that the first order derivative vanishes. So for that, what I'm going to do, so this implies I can write it as your v u double prime, and then let me come to first order derivatives of u prime. So I'm going to get from here, see, I'm going to get 2v prime plus here this px v. Just a minute. I have done with this part. I have done with this part. I have done with this part. Yes, into u prime, and then I am left with the other 3 terms. I'm left with the other 3 terms. This is v double prime plus px v prime plus ux v into u. This is equal to 0. Okay, fine. See, what I'm trying to do, I'm trying to reduce this equation into this form. Okay, so in order to achieve that, what I must have, I have to plug in this to be equal to 0. Okay, fine. So uh, let us choose your 2b prime plus px v equal to 0. Okay, so then this is going to imply px, and from here I am going to get your okay, fine. Yes. So this is classical. See again that constant of integration I am not writing down because that is not going to affect the final outcome. Okay. So this is e to the power minus half this px dx. Okay. Fine. So then under these circumstances, what will happen to this term? So from here, you have already seen that from here I can write v prime equal to half pv, right? Minus half pv. Is it okay, everybody? Fine. Okay. And then v double prime. So this is going to be equal to half p prime v minus half p v prime, and again minus half p v prime is minus half p v. So then this is equal to minus p square v. Okay, fine. So therefore, what is going to happen? So therefore, see, I'm concentrating on this term. Therefore, your v double prime plus pv, say I can write it like this, plus pv prime plus qv. So v double prime was minus this v plus 1 by 4 v square v, and p v prime is going to be equal to minus half p square v, because v prime is minus half pv. Okay, and then plus qv. So I can simply write it as your, I'll write this first, say positive term qx minus p prime x by 2 v, sorry, p prime x by 2, and then from these two I am going to get minus 1 by 4 p square v. Okay, so that means if I call this term as qxv, right? Sorry, that term under the parenthesis I call it small qx. So then what is going to happen? Under the assumptions that we have taken, that we have assumed that this is equal to 0. So then what is going to happen? This is going to reduce to simply this, and here instead of this, what we have got qxv, isn't it, from this term? Okay, so eventually my equation is going to reduce to u double prime small ux u equal to 0. Okay, is it okay with everybody? Fine.
Yes, sir.
So basically, what we have done some mechanical stuff. So this is all about, I mean, simply, this is all about simply you're converting this just a moment. See, why we can divide it by v? Say here in this equation, we have divided by v, isn't it? Why is that permissible? V cannot be 0, right? Why?
Because it is in terms of exponential.
You don't even have to think about it. Say v, where did v occur? We assume that y equal to uv, isn't it? So if v is equal to 0, so then y will be equal to 0, right? And we are not considering the trivial solution, remember. Okay, see here our aim is to study the oscillatory solutions. If at all the solutions are oscillatory, if at all the solution has some 0, is it okay? Fine. So if the solution has some 0, right, then what it must have? What it must have? See, we are not interested in the 0 solution. That is the first thing. I want the solution curve to cross x-axis at least once somewhere. Fine. Okay. So that is why I'm going to assume that v is not 0 because I'm not interested in the trivial solution. Okay. Fine. So basically, what we have done. So simply we have reduced. This into something like this. Okay. So now you tell me. I mean, how is that going to help me? How is that going to help me? Yes. See, okay, let me give you one more. See, I am trying to study the nature of the solution of this equation 1, right? And the solution I am going to call it yx. Okay, fine. And the nature of the solution means I am simply interested in the zeros of y. Is it okay? Fine. Then from here, if I study this equation, its solutions are going to come as ux. Fine. So far so good, right? But what is yx? What is yx? Yx is equal to vx into ux, right? Okay. Fine.
Yes, sir.
Yes. Now I have already told you that I'm not going to assume v to be 0. I'm going to assume v to be non-zero, to be precise, right? Because if v equal to 0, I mean it doesn't serve my purpose, right? So if v is non-zero, then what is going to happen? The number of zeros, the function u is going to show will be the same as the number of 0 of y, isn't it? Fine?
Yes, sir.
Yes, sir.
Yes, isn't it? It is only a matter of scaling. It is only a matter of scaling. Is it okay? Fine? So basically, what is going to happen? You consider something like, say suppose this is say something like an oscillatory solution like sin x. Okay. So then if I multiply this function is say ux. If I multiply this function with a function say vx which is non-zero, so then at most what it can happen, it is going to have something like this, isn't it? But they are going to cross the x-axis at the same points, isn't it?
Yes.
If I have this situation, are you getting my point? Right? Both these functions are going to give me the same zeros, and they are going to follow the same oscillatory behavior, right? So that is why if I study this equation, if I study the solution of this equation, it suffices for studying the solution of this. Now is it clear?
Yes, sir.
Yes, sir.
Yes? Okay. So that brings me to the second theorem about this qualitative behavior of solutions. Okay. So what is the second theorem? So let me show it to you, and then again, as before, I'm going to explain it, and then I'm going to prove it. And this is very straightforward, this second theorem. This one. Okay, this theorem B. Please have a look at that. Theorem B. Okay, this is theorem B. And it is very straightforward. You have a look at that. For the time being, let me just erase the black hole. And ux is a non-trivial solution of this equation. Zero. So let me call it 1. Then ux has, remember, at most 1, 0. Okay, at most. So that means it may not have any 0 at all. Right? So suppose if your solution is of this form, say x squared plus 1, right? This function has no 0. The curve is always going to lie above x-axis, 1 unit above x-axis. Is it okay? Fine? Something like that. Okay. Okay, fine. So again, now we are back to square 1. But here, I have one more auxiliary relation here. Even though right now you may not be noticing it, that relation is going to help me in determining my conditions. Okay. So let me try to do the proof. Okay. Right. So proof. Okay. Right. Say, suppose x naught is a 0 of u. That means u x naught equal to 0. ux not equal to 0. Okay. So now from here, one interesting observation is going to come. Okay. So now ux naught, it cannot be equal to 0. Ux naught cannot be equal to 0. Why? Can you tell me why?
Then u will be identically 0. But
How?
ux is non-trivial solution given.
No, why? I mean, this. Why u will be identically 0?
We have seen the uniqueness in existence theorem earlier.
Exactly. So that is where the clue lies. Okay. See, if I consider the neighborhood of x naught, so then what is going to happen? If your u x naught is going to be equal to 0, so then by the continuity of u, what is going to happen? So ux is going to be equal to constant in the neighborhood of x naught. Okay. Now I have been given two conditions here. So that means I have been given two conditions here. This is equal to 0, ux not equal to 0, right? So under these two conditions, I mean, whatever may be, it doesn't necessarily have to be 0 everywhere. Okay. Say, suppose I have something like lambda 1, I have lambda 2, this is equal to lambda 1, this is equal to lambda 2, right? So under these assumptions, what is going to happen? This equation is always going to have a unique solution. But you know, u equal to 0 is already a trivial solution, right? Isn't it? If it is a unique solution, then because this is a ux equal to constant, that trivial this solution must be the 0 solution, right? Which we have assumed that u is non-trivial, right? We get a contradiction. So that is why we are assuming that u prime x is not equal to 0. Okay. So now let us assume that your u, because this cannot be equal to 0. Let us assume that u prime x naught is greater than 0. U prime x naught is greater than 0. Okay. So now let me try to visualize the situation here. So today I forgot to fine. So suppose this is my x naught. Suppose this is my x naught. Okay, and over here, the value of u is 0. And again, if u prime x naught is greater than 0, at this point, the function u, it has to be monotonically increasing. Is it okay?
Yes, sir.
Fine. So that means the curve must rise here. The curve must rise here, isn't it?
Yes.
Right? The curve must rise here. So if it rises, it has to rise above this x-axis, right? So that means your ux is greater than 0 over for x line to the immediate. I am using this for immediate, although it is not in book they have used immediate. I am using it. Immediate right side of x naught, isn't it? Okay. I'm not bothered about, I mean, when x is tending to infinity. For the time being, I am only interested in this neighborhood of x naught, to the right neighborhood of x naught. Is it fine with everybody till now?
Yes, sir.
Yes, sir.
Yes? Okay. So now, see, I have been telling you about having an extra auxiliary relation here at hand, which is going to help us in proving the theorem smoothly. Okay. Now look at the original differential equation here. Look at the original differential equation here. So then, from the differential equation, what we get? U double prime, that is equal to minus qx ux. Okay, fine. And what is the very first condition? Qx is less than 0, right? And we have already found out that ux is greater than 0. So that makes u double prime to be positive, right? In the immediate right neighborhood of x naught. Are you getting the point?
Yes, sir.
Yes, sir.
Yes, yes, right? See, this is positive. Since qx is negative, the whole thing is positive, positive, positive. This is eventually positive, right? So that means what is happening to my curve u, or what is happening to the curve u prime? So that means u prime is monotonically increasing, right? Or this u double prime positive means that u is concave upwards. U is concave upwards. So this curve must go up like this. This curve must go up like this. Isn't it? If it goes up like this, it is not going to cross the x-axis, right? So that means it cannot have any 0 toward the right side of x naught. Similarly, by the same argument, we can prove that it cannot have more 0 towards the left hand side of x naught. So that completes the proof. Is it okay? Yes? Yeah. So this is about theorem number 2. Now, can you give me something more from that auxiliary relation? Yes? There should be still one doubt there, because I say that immediate neighborhood. I use the word immediate neighborhood. Right? What happens when x is extremely large, x tends to infinity? Immediate neighborhood, I know that it is going to simply rise up and up and up. Why? I mean, why? Like say it cannot come down. Why the curve cannot come down?
If it come down, then u dash will be negative.
U prime will be decreasing, right? So that means I have to have a concave downward curve. But another thing, say I am having something like this, okay? So at some juncture, say this is concave upwards, this is concave downwards, right? At some juncture, I should have something like that. That means I must encounter a point of inflection there. Is it okay with everybody?
Yes, sir.
Right?
Yes, sir.
Yes. Now, can you tell me, this is not going to happen. This is not going to happen because, like say, you go on increasing the neighborhood using the continuity of the function, it is going to be increasing and increasing and increasing like that, u prime. Okay. Now, if at all you can get a point of inflection, where can you get that? Yeah. Yes?
At that point, either Q is 0 or U is 0. The point of inflection.
Where is, yes, and
But Q
U is 0
is
where?
negative.
U is 0 where? I definitely have a point of inflection here. I definitely have a point of inflection here. Where is that? Right? No, I'm asking you about, I mean, while proving the theorem. I assume that U was 0 here, right? Isn't it? So if you plug in this, then U double prime x naught is going to be equal to 0. So the only possibility here in this particular case, it is going to lie here. Is it okay? Fine. In this particular case, that could be the only possibility. Because see, we are going to make use of this fact. I mean, later on, in some cases, we are going to do that. Okay. So I still have another 4 minutes. I'm going to consider this equation in one of my exercises later on. Okay. So please, can you solve this? Can you solve this equation? Or there is a significant value of k, or a specific value of k is very important. Can you find that out for me? I mean, if you have to solve this equation, how can we proceed it? Yes?
So x square multiplied by x square, then put it z is equal to log x and converted it to
So it is
constant coefficient.
ky, this is going to be 0, right?
Yes, sir.
Okay, so what you are saying is that to be transformation something like this, you are going to
Yes,
convert it into something like d into d minus 1 plus k y, this is equal to 0, where d now stands for d dt.
Yes, sir.
Okay, so I have given you enough hint. So can you give me that significant value of k? What I am looking for, because I would like to give you the answer to one particular question which we are going to encounter later on, okay, by using this example. So basically this is auxiliary equation is
Its roots
right?
depends on value of k. So
Yeah, I am
for
trying to take some significant value of k, I mean specific value of k, which is going to be significant.
okay,
What
sir.
could be that? See, from here, right? So now, are you getting my question properly? So that significant value of k is what?
If
Should
whole
be
k
less
less
than
than
1 by
1, then
4.
it's real.
So whether k is greater than 1 by 4 or less than
Or
equal to
less
1 by 4, right?
or exactly 1 by
1 by 4, the solution is going to, the nature of the solution is going to depend upon that. Okay, so tomorrow's class, I'm going to bring this back. Okay, so that in when I'm going to bring this back, then I'm not going to discuss about the solution procedure. Okay, I directly move to that. Okay, fine. So tomorrow I'm going to prove a couple of more theorems related to this qualitative behavior of solutions of ODEs, and probably power series also I'll be able to cover a little bit of that. Okay, so then I'll meet you tomorrow.